name is Chris Leona Mongin, 07DKA24F1124, will explain what is momentum. So, in fluid mechanics, momentum is essentially the quantity of motion of the fluid. Just like a solid object, a moving fluid has momentum, which is its mass multiplied by its velocity, which is rho equals to mass multiplied by velocity. However, because fluid is a continuous flow, we usually talk about the momentum flow rate, also known as momentum flux. This is the amount of momentum passing through a certain area per unit of time. The most important concept is the conservation of momentum, which is a direct application of Newton's second law, F equals to mass multiplied by acceleration. For a fluid, this law is stated as the net force acting on a fluid volume is equal to the rate of change of momentum of that fluid. This means that if you want to change the fluid's velocity or direction, for example, to change its momentum, you must apply a force.
For this presentation, we choose question 2. In this question, we have a bent plate that deflects a water jet with a diameter of 80 millimeters. The jet strikes the plate with a velocity of 40 meters per second and it gets deflected through an angle of 44 degrees. The plate is assumed to be stationary, meaning it does not move when the jet hits it. Because of that, the force of the water is completely transferred to the plate. What we need to do here is to find the x and y components of the force that the jet exerts on the plate. So basically, we are calculating how much force acts horizontally and vertically due to the change in momentum of the water jet. In simple terms, this question is testing our understanding of momentum principles in fluid mechanics. Thus, our main goal is to determine the values of Fx and Fy. Now let's look at step 1 of the solution. From the question, we know the jet diameter is 80 millimeters and the velocity is 40 meters per second, and the angle is 44 degrees. First, we change the diameter to meters, which is 80 millimeters divided by 1000 equals to 0.08 meters. Next, we find the area of the jet using the formula pi diameter squared divided by 4. When we put in the values, we get 5.03 exponent negative 3 square meters. Then, we find the discharge, which is the flow rate of water, so discharge equals to area times velocity. Then we will get 0.201 cubic meters per second. This means 0.201 meter cubics of water hits the plate every second. We'll use this value in the next step to find the force.
From figure 1, water flows horizontally into a band at 40 meters per second, then exits the band upward at 44 degrees to the horizontal, also at 40 meters per second. The aim is to find the force exerted by the fluid on the band or by the band on the fluid along the x-axis. So we must take into account the density of water, which is 1000 kg per meter cubic, and the discharge from previous calculation, which is 0.201 meter cubic per second, and the velocity given is 40 meters per second, as well as the angle given, which is 44 degrees. So, for steady flow, the rate of change of momentum in the x direction gives the force Fx equals to rho q multiplied by the difference of Vx1 and Vx2, where Vx1 is velocity component of inflow along x-axis, while Vx2 is velocity component of outflow along x-axis, while q is the discharge of volume flow rate and rho is the fluid density. So for the step 2, we must take note that the Vx1 is the inlet or horizontal which is 40 meters per second, because the flow enters purely along the x-axis, while the outlet is at 44 degrees, which is the Vx2. We must find it by 40 multiplied by cos 44 degrees. Cos 44 degrees is 0.719. So we must multiply it with 40. And we get the answer 28.76 meters per second. Next, we must substitute the answers into the momentum equation, which is the Fx equals to rho q multiplied by the difference of Vx1 and Vx2. So we must substitute the 1000 for the water density, 0.201 for the discharge, and 40 for Vx1, and Vx2 is 28.76. So we need to subtract 40 with 28.76 and we get 11.24. So we need to multiply rho q and the difference of Vx1 and Vx2, which is 100 multiplied by 0.201 multiplied by 11.24, and we get the answer for Fx is 2259.24 Newton. This value Fx 2259.24 Newton represents the net horizontal force required to deflect the jet from horizontal to 44 degrees upward. The arrows to the right indicates the force direction along the positive x-axis that is acting on the fluid.
Alright, so in step 3, we are calculating the force exerted along the y-axis, which means we are finding the vertical component of the force. You will times 1000 times 0.201 times 40 minus 40 sin 44 degree, and then you will get 1000 times 0.201 times 0 minus 40 times 0.695. The results in 1000 times 0.201 is 2001, and then you will times it with 0 minus 27.8, and the result you will get negative 5,587.8 Newton. So to summarize, the vertical force acting on a jet is 5,587.8 Newton downwards. This means the water exerts a strong downward push due to the change in the vertical velocity component. So to summarize all, referring to the calculation that we have done, we came to a final answer where force exerted along x-axis is 2,256.508 Newton to the left, while force exerted along y-axis is negative 5,585.053 Newton downward. Thus, we have answered the question.